Hi, the section 8.1, async group proportions. The question, so is 105 males out of 200 babies significantly different from 50%? So the idea to answer this question is simulate 200 observations many times with assuming that 50% is male. Then after that, we see if our realization 105 over 200 is unusual or not. So each time we generate 200 observations, and many times, like 1,000 times. So in total, we have the 200 times 1,000. So we generate basically the 200,000 binary random variables there, which represents either male or female. And this is the simulation result in our language. And this is the simulated the proportion of males among 200 babies if P is equal to 50%. So since the true probability to have male baby for each observation is 50%, on average that we have the 50% male. And you can see that these have the 10 bins. So actually with this, yeah, I think that I have generated probably the 100,000 times. So the about maybe out of the 100,000 times, maybe 10,000 times that we will get the p hat proportion of male between 50% and 51%. And a little smaller probability with a little smaller probability between 0.51 to 0.52. And so on. And you can see 0.525, our sample proportion is here. So it's not really the unusual. So it's kind of a range of typical value. So we can conclude that the 105 over 200 is not significantly different from 50%. So to be exact, if we have the threshold, that we have a significance level, then we will define some threshold. Then if the observations are unusual, then we reject null hypothesis. So typically that we take the area of 0.05 and that we reject null hypothesis if p hat is above this line, maybe 0.57 or something, or p hat is too small, maybe 0.38 or 0.42 or less, maybe, or 0.43 or less. So we decide that with this rule. But this is just an idea, and we can develop more the exact formula using statistical theory. So a statistical view is that the proportion of males in 200 babies is a random variable. So even if we have true probability p, so every time that we have some randomness, so p hat maybe 0.508 or 0.482. So this is random variable. And the p hat is approximately normal by central limit theorem, because the p hat is basically the average of 200 observations, and each observation is either 0 or 1. Maybe the 0 means female and the 1 means male. So that is the average. So each xi is either 0 or 1 with 50% probability, and the p hat is a sample mean. And x1 to x100 are independent and identical random variables. So p hat is approximately normal. So to see the distribution of p hat, we have simulated it, but this becomes normal, and the expectation and the variance also we can calculate it. So if we know this information, then we can just derive the distribution of p hat statistically. So we don't really have to do simulation every time. Yeah, so for the complicated tests, actually we simulated the two tests. So that is common procedure. But for this kind of the simpler situation, the statistical theory that works better. Okay, so we want to get the expectation of p hat and the variance of p hat. So at first, think about the simplest case. So that is the sample size is 1. So 200 babies are too hard to handle with. So consider a case of 1 baby first. And the write x instead of p hat. And suppose that the probability of male is p naught. P naught is 0.5 in the above assumption. And x is equal to 1 with probability p naught. And the x is equal to 0 with probability 1 minus p naught. Then what's the expectation of x? So x is basically the indicator for male. And what's the expectation of x? In the common sense, you can see that is p naught. Or you can say that this is equal to summation of all possible value of the xi times the probability of xi. So probability of xi is here, and the possible values are here. So possible values are 0 and 1, and the probabilities for those are 1 minus p naught and the p naught, respectively. So expectation is equal to p naught. And how about variance? So we can calculate the variance in the same way. So variance, by definition, the summation over I of xi minus expectation of x square times p of xi. So p of xi part is the same as the previous one. So it's a 0 or 1. So 0 for with probability 1 minus p naught and 1 with p naught. Then the x minus the expectation of x. So this is the 0 minus p naught and 1 minus p naught and the square. So if you just simplify it, then we can get, okay, so actually the 0 minus p naught is p naught square, and to simplify it, then we get the p naught times 1 minus p naught. So this is the case for one observation. How about multiple observations? So in general, let's think about we have n babies, and p hat for n babies is written as x1, the summation of x1 to xn over n. So again, the xi is equal to 1 if male and 0 if female. So 1 with probability p naught and 0 with probability 1 minus p naught. Then expectation of p hat is just the n terms. The expectation is linear. So the n terms, the summation of expectation of xi's divided by n. So that is n p naught over n, so p naught. Of course, if we have many observations, still on average that we have the same proportion of success. So we have the p naught here. But the variance of p hat is different. So you know that if we have a larger sample size, the result is stable. So if the true probability is 50% and if we only have the 5 babies, the 5 observations, sometimes all babies are male or all babies are female. But if we have the 500 observations, probably numbers are close. For example, maybe we have the 260 out of 500 male, or maybe 238 male out of the 500. So it's not 0 or 500. So it should be more stable. And how about, actually, what's the exact value of the variance of p hat? P hat is the summation of xi's over n, and the variance is a squared quantity. So remember that at first, the variance of a times x is equal to a squared times variance of x, because variance is squared quantity as seen in the last slide. So if we have a here, a times x, then a square comes first. So variance of x1 over n, for example, becomes variance of x1 over n square. How about summation? So summation, the variance of x1 plus x2. So this becomes variance of x1 plus variance of x2 if both are two variables are independent. Okay. The first one is always true, but this second question equality holds if the x1 and x2 are independent. Sometimes independent, we use this symbol, independent. And so we can decompose this ones. So the variance of x1, the summation of xi's is equal to the summation of variance of xi's. So each term is p naught times 1 minus p naught, as seen in the previous page, and the over n square. But we have n terms, so n square becomes n. So this is the variance, p naught times 1 minus p naught over n. So using these two properties and the fact that p hat is approximately normal, that we can do testing. So theorem, the test statistic z is defined by p hat minus expectation of p hat over standard error of p hat. So that should follow approximately the normal distribution with mean 0, standard deviation 1, variance 1. So that is p hat minus p naught. P naught is the probability under the null hypothesis in the previous example 0.5 over this one. And this one is obtained by just the p naught. So hypothetical, the true parameter. So if p naught is 0.5, just you can plug in p 0.5. And the z has normal distribution. So if this test statistic fall in the extreme range of this standard normal distribution, we reject null hypothesis. So if the z normal 0, 1, so this is distribution of z, then if that falls in this extreme range, either on the right end or left end, then this part and this part, we reject null hypothesis. That the p is equal to p naught. And otherwise, we accept. So that is the single proportion, the test for single proportion. So this hypothesis, null hypothesis, is rejected against the two-sided alternative if the absolute value of z, example z here, absolute value of z is larger than the threshold. And actually, okay, so we are assume that this area is alpha over 2. Here, alpha is the significance level, typically 0.05. And if the absolute value of z is larger than this value, so this value is defined as the z sub alpha over 2. And this value is the z sub 1 minus alpha over 2. So if the absolute value of z is larger than this value, then we reject null hypothesis. Sometimes we have one-sided test. So alternative hypothesis is one side of null hypothesis. So in this case, okay, so typically, okay, so p is equal to 0.5 against p is larger than 0.5. So we reject only if the p hat is large enough. So in this case, the null hypothesis, the rejection region is only for the right side of the distribution. So the if this is the distribution, normal 0, 1, and the one-sided test, then we have a slightly larger area. So this is the area of alpha, and we reject null hypothesis only if this z value is larger than this threshold 1 minus, sorry, the 1 minus alpha, z sub 1 minus alpha. That is the point at which the probability above that point is equal to alpha. So z sub 1 minus alpha. So this is rejection region. And the other way around is similar. So H1 maybe the p is less than 0.5. In such a case, we only reject null hypothesis if the z value is small enough. So this is the theory, the general theory for the test for single proportion. So next time that we will have an example for this theorem.